So, our previous case, we talked about the interference of wave on the string for the wave that moving to the same direction, right? In this case, we're going to deal with the wave that moving in the opposite direction. Um, think about the interference of wave that one is the incident wave and another is the reflected wave. Okay, so let's go back to the previous slide that we talked about the reflection of the wave on the string. That seemed like I mentioned about losing end and fixed end, but I didn't mention about what really you get from the reflection. For the losing end, what we're gonna get is the wave that reflect back. You see, you have an incident pulse moving to the right, and you get the reflected pulse moving to the left, and this reflected pulse get you the same wave. Same means that it remain the same phase. So I can say that no phase shift for the case of losing end string. But for the fixed end, you get the incident moving to the right and the reflected moving to the left, but you see that the phase of the reflected pulse is shift. So I can say that it's phase shift by pi radian, or you get the opposite phase. Okay, uh, okay, that what important for the next part that we're going to talk about. Okay, now there should be two cases when you think about, okay, you want to deal with the interference of the wave or that travel, uh, I mean incident wave and opposite wave. The possible case to get the wave travel to the opposite direction is that incident and reflect, right? Okay. Um, in this case, so we deal with the losing end case. What you get is the incident wave kx minus omega t. So in this case, ym psi kx minus omega t for the incident wave. The reflected wave for the losing end, you know that is not change the phase, so you get the same phase as the incident one. But reflected wave, in this case, it just change the sign from in this case negative side. You know that moving to the, it means that the wave moving to the positive x direction, right? It just change the sign to from negative to positive, means that now you get the same wave, but it's moved to the negative x direction. You do the same thing, you know, this is quite simple. You get y1, y2, so you just sum up to find this resultant wave. And what you get in this case is something like this. You can try by yourself. It's not difficult. Okay, you know that you can use this mathematical formula to find the combination by yourself. Okay, I'll just skip how to come up with this function, but anyway, you know, it's quite easy. Okay, all right. So what you get now is different for the case a bit from the case that the wave moving to the same direction, because I just remind you, when you deal with the case that wave moving to the same direction, so let's say two wave moving to the same direction, in this case is positive x, so the resultant wave get you to ym cosine half of the phase different and multiplied by psi kx minus omega t plus half of the phase. This is for the case that we're moving to the same direction. but for the you can compare. So what different? First things is you see that kx and omega t are split into different functions. You have one sine, one cosine. Uh, they're not in the same. What means by that? And I just mentioned before, if we go back to the previous slide, um, I just mentioned before that um, this part is the amplitude, right? New amplitude, and this part is a wave characteristic or continuous wave characteristic. If it's not exactly like this, so I mean when uh, kx and omega t split in different function, what you get is not the continuous wave you know anymore, but you might feel familiar with something like, okay, cosine omega t or sine omega t, right? Think about the simple harmonic. Simple harmonic, you deal with something like y or t equal to ym cosine omega t, right? This is a characteristic of simple harmonic. Apparently, cosine omega t or sine omega t is a characteristic of simple harmonic. You know that. But what is this 2ym sine kx? Okay. When you consider a particle on the string at x position, this will become the amplitude of the simple harmonic. What I mean to say is, what you get from the combination of this wave is a series of simple harmonic motion. So you know that you have, for example, like this. You have like a string and a particle at different x position, like this, and all of them moving up and down in simple harmonic motion. Any position moving up and down, but different phase. What I mean to say, why different phase? Not different phase. Sorry, I should not say that. Different amplitude depending on x. They move with the same phase because of course they has the same cosine omega t, right? But in this case, their amplitude depending on 2ym sine kx. You know, if you put the value of x in, you know what is the amplitude of that simple harmonic particle in the x position. Okay, that actually is. So I believe that you understand what I mean. Okay, and this 2ym sine kx has periodic properties, mean that when it's complete, you know that k equal to 2 pi divided by lambda, right? When the value of x start from 0 up to lambda, so from x equal to 0 to x equal to lambda is complete one cycle, right? It will start from x equal to 0 again, because this is a property of psi function. Okay, well, I will show you the animation later in the next video, but now, okay, let's try to understand what really it is. I can say that this will give you a difference interference. I mean this the amplitude of the simple harmonic here, that equal to 2ym psi kx, you get the different result of the interference depending on x. Okay, so let's say in this case, if psi kx equal to 0, you want to find the node or fully destructive, right? Position. You just say, okay, my ym here should equal to sorry, y my y prime xt equal to 0. That means psi kx should equal to 0 and kx equal to n pi. And that finally means that if you say, okay, my k equal to 2 pi divided by lambda, you can find the x equal to n lambda divided by 2, and for n from 0, 1, 2, 3, and so on. That is the position of the node on the string, and this is actually called standing wave. I should mention that you in the animation you find that the wave, I mean, not moving, but it seems like it's just moving up and down. Okay, and you can find also the position of the antinode, or when it get you fully constructive interference, or y prime equal to 2ym, and in this case is corresponds to psi kx equal to 1, or you can really say that absolute value of psi kx equal to 1. Okay, I should delete this. Okay, all right. And instead that kx equal to half the pi, or 3 pi divided by 2, 5 pi divided by 2, and so on. And you can really get the same form for the antinode position or fully constructive interference. Okay, in this case you get antinode or fully constructive, right? All right, for the next case, the interference of wave on to fixed end. You see, this case you have the incident wave the same as the previous case, so moving to the positive x direction, and you suppose to get the reflected wave to the negative x direction, right? The difference between these two fixed end and loosened end is that the reflected wave should have the phase flipped by pi radian, and that only different. And what you get by the same way, you use a mathematical formula to combine two psi function, and then you get this function in the end. And similar to the previous case for the loosened end, that what you get is not the characteristic of the traveling wave, right? Like I mentioned before, if the kx and omega t is not in the same function, so this is not traveling wave, and it's standing wave. And when you compare with the previous case, this one, you see that it's like I mentioned, sine and cosine theta are the same things, only have some phase different. So you can say that for the case of loosened end and to fixed end, you get similar thing. So actually you can say that it's the same thing with some phase different. Okay, that's what I want to make a conclusion. All right, so next, like I mentioned, you can also define the wave, let's say incident wave, as a cosine function, and in this case you will get the reflected wave also in the cosine function with the phase shift, right, and travel to the opposite direction. Let's try by yourself using this formula to combine the cosine function and get the resultant wave. Okay,